Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we are going to talk about the Fisher projection, but before we do so, I want to go over the answers to these learning check problems that ask you to identify all of the chiral carbons that's found in the following molecules. And so I went ahead and worked on the first five molecules that's found on this slide in the previous lecture video. The only one that I wasn't able to do is this last structure. And so this molecule only has one chiral carbon, which is going to be highlighted in pink. And so for the next lecture, for the next slide of this learning check, these two molecules we went ahead and did in the previous lecture video. Just a quick note, depending on what you guys are looking up, your sources, etc., if you guys come across the word meso, please ignore it completely. That's going to be for the full year of organic chemistry. We are not going to deal with meso compounds or meso, so M-E-S-O. If you guys ever come across that term, go ahead and completely ignore it. And so for this molecule right here, there are no chiral carbons, and Me is just a shorthand notation for methyl. Okay. In the last slide, everything in pink that you guys see are locations of chiral carbons. For part D, I didn't mark anything because I kind of want to quickly go through it. I didn't talk about how to identify chiral carbons for cyclic alkanes in the previous lecture video. So I want to go ahead and quickly do an example. And so I'm going to go ahead and start off by identifying or by filling in all invisible hydrogens for each carbon. So there's quite a few here, so it's going to take me some time. And so remember, when you guys are filling in your invisible hydrogens, you want to make sure that the carbon that you're looking at has 4 covalent bonds. So if it has more than 4 covalent bonds, you've added way too many hydrogens. If it has less than 4 covalent bonds, and I'm talking about the combination of single, double, and triple bonds, then you guys didn't draw in enough hydrogens. All right, and so what I'm going to do is I'm going to start erasing carbons that are achiral. Okay, and once again, if a carbon has 2 or more of the same substituent attached to it, then it's going to be achiral. And so this carbon is achiral. This carbon is achiral. This carbon right here is achiral because it's attached to 2 methyl groups. Okay, so I'm going to erase that. So this carbon is chiral, and I'll talk about why in just a second. This carbon right here has 2 hydrogens, so that's not chiral, not chiral, not chiral, and not chiral. And so it looks like there's only 3 carbons that have chiral centers, have chiral carbons. And so when you guys are working with chiral carbons that are part of a ring, what you guys are looking for is whether or not that ring is symmetrical or asymmetrical. And just because you guys have 1 hydrogen on these carbons, that doesn't always mean that carbon is going to be chiral. And so you want to check for symmetry for cyclic compounds. And so I'm going to go ahead and just erase these 2 hydrogens for now. And I'm just going to go ahead and focus on the carbon that I've highlighted in pink. And so this carbon is connected to a hydrogen, so that's one unique substituent. And this carbon is connected to an isopropyl, so that's another unique substituent. It's different than just a hydrogen. And so when you guys are dealing with the remaining two bonds for cyclic compounds, what you want to do is I'm going to go ahead and change my colors here. Feel free to just like cut it in half. So hopefully you guys can see the green on your screen. Actually, let me do something. Let me do orange. And so I'm going to go ahead and cut it in half. And so I want you guys to see that if you follow the bond in orange, notice what I've highlighted is going to be not, there it is. It's going to be completely different than the other side, right? And so because the left and the right are asymmetrical with respect to the orange and the green that I've highlighted, then there are technically 4 different substituents on that carbon that's highlighted in pink. And so therefore, that carbon is going to be a chiral carbon. Okay. Cool. So we've identified that this guy is a chiral carbon. I'm going to go ahead and erase it for now. So let's go ahead and look at this. We're going to go ahead and look at this carbon. Remember, there's one invisible hydrogen. Here we have 1, 2, 3, 4 bonds. And so what I'm going to do is I'm going to, just kind of draw a line. And so I'm going to observe whether or not the left and right side are symmetrical. See here, I think I kind of jumped the gun on this one. So let me backtrack. And so first and foremost, let's go ahead and focus on this carbon. So this carbon has, it's attached to this hydrogen. So that's one unique attachment. It's attached to this OH. So that's another unique attachment. And so when you get to the left and right hand side of the bonds with respect to this carbon, then you guys are going to draw that orange line that I previously erased. And you guys are going to look at the left and right side with respect to the carbon that I've highlighted in pink. And so notice that if you look at the substance, if you look at the stuff that's on the left of the orange line, it's going to be completely different than the right side of that orange line. And so therefore, in total, the carbon that's highlighted in pink, that's currently highlighted in pink, will have 4 different substituents. Okay. All right, so let's go ahead and look at this carbon. So we have one invisible hydrogen, so that's one unique attachment. This methyl group is another unique attachment to that carbon that's in blue. And so what I'm going to do is I'm going to go ahead and cut, I'm going to create a line, and I'm going to determine whether or not I have a symmetrical molecule with respect to this carbon that I've kind of marked in blue. And so if I look on the left side, if you will, notice that it's different than the right side. And so that lets you know that this carbon right here has 4 unique attachments. Okay? The one that I've circled in blue and the piece that I highlighted in green, and the piece that I highlighted in red. And so overall, I have 3 different chiral centers. So I have 3 chiral carbons for this molecule. Now, if you guys are looking at this molecule, letter F, okay. Actually, let's go ahead and look at letter E. And so here there's 1 hydrogen. And so if we're looking at this carbon, we have 2 unique attachments. And so I'm going to go ahead and draw a line, cut it in half, so to speak. And if you guys are looking at the right-hand side, and if you guys are comparing that with the left-hand side of that orange line, notice that both sides are different. And so therefore, there is technically 4 different substituents with respect to the carbon that I highlighted in pink. So therefore, that carbon is going to be chiral. Okay. And so if I were to look at this carbon right here, right, so these are very similar molecules, E and F. One might think like, oh, you know, this there's a chiral center. And so once again, I can go ahead and just circle my substituents that are unique. Hydrogen is different than chlorine. Insofar, I have 2 unique substituents. And so if I were to draw a line, an orange line that kind of cuts this ring in half, and if I were to, look on the left and right side of this orange line that I just made, I want you guys to note that both the green and the red highlight are exactly the same. And so because there's symmetry in this cyclic ring, the carbon that I've highlighted in pink is achiral. It is not chiral. So overall, there are no chiral carbons for letter F. Same thing for letter G. And so for letter H, once again, if I draw that orange line, notice that there's asymmetry in this cyclic ring. And so therefore, those carbons that I highlighted in pink are going to be chiral. They will have 4 different substituents.